Good morning, everyone. This video we are going to talk about inverses of matrices, section 10.5. In previous videos, we have covered the addition of matrices, the subtraction of matrices. How do we multiply a matrix by a number? How do we multiply two matrices? By the way, we don't cover division of matrices. Even it is a important concept in matrix theory, but we don't cover that. Instead, we are going to talk about the inverse of a matrix. So that's the section 10.5. We start from the definition of identity matrix. How do we define identity matrix? Identity matrix is a square matrix, means the number of rows and the number of columns of the matrix are equal to each other. If we have a 2 by 2 square matrix, the entries on the main diagonal are ones, and the other entries are 0. Then this matrix is an identity matrix, 2 by 2 identity matrix. What if we have a 3 by 3 matrix? The main diagonal, all the entries in the main diagonal are ones. All other entries are zeros. Then this matrix is an identity matrix with the size 3 by 3. So you can imagine or you can guess the identity matrix with a higher order. Generally, if we have a n by n matrix, square matrix, the number of rows and number of columns are n. N could be any positive integers. And the entries on the main diagonal are ones. And all other entries are zeros. Then this kind of matrix are called identity matrix. I think I'm clear enough, right? Okay, so in a number set, number 1 is the identity. We can think about any number, let's say 10. Any number multiplied by 1 equals the original number, right? In other words, in multiplication, the identity number, the number 1 doesn't contribute. Same idea here. Identity matrix doesn't contribute in multiplication of a matrix either. For example, we have a 2 by 2 because 2 by 2 has a lower order. So we're going to take that as an example. You can get the same result for a higher order matrix. Let's say we have a 2 by 2 matrix, 1, 2, 3, 4. We multiply this matrix by the identity matrix, 1, 0, 0, 1. This multiplication is well defined because this is 2 by 2. This is also 2 by 2. The number of columns of the matrix on the left equals the number of rows in the matrix on the right. So the multiplication here is well defined. So if we apply the definition of the multiplication of two matrices, we covered that in previous video, section 10.4. We have row 1, column 1, that is 1 times 1 plus 2 times 0 gives us 1. Row 1, column 2, 1 times 0 plus 2 times 1, that is 2. Row 2, column 1, 3 times 1 plus 4 times 0, 3. Row 2, column 2, 3 times 0 plus 4 times 1, 4. You see what happened? This identity matrix doesn't contribute anything, means it just like number 1. It's just like you multiply by number 1. So in the multiplication of matrices, identity matrix is just like a number 1. You understand what I'm saying here, right? Okay. So we have the concept for identity matrix because we need that definition for defining inverse of a matrix. Not every matrix is invertible. It's just like not every number is invertible. For example, 0 is not invertible because the reciprocal of 0 does not exist. But a non-zero number is invertible. The reciprocal of the number also can be written as a to the power of -1 is the inverse of the number in a sense. Similarly, if we have a n by n square matrix, by the way, if the matrix is not a square matrix, in other words, the number of rows and the number of columns are not equal to each other, then the matrix is definitely not invertible. So when we talk about inverse matrix, we are talking about square matrix. Square matrix, okay? Yeah. So let's say we have a n by n square matrix. Is a matrix if the determinant of the matrix is non-zero, then we say the n by n invertible, the n by n square matrix A is invertible. Invertible means the inverse of the matrix exists. One more time. If the number of columns and number of rows of the matrix are not equal to each other, then the matrix is definitely not invertible. That matrix definitely has no inverse at all. So we only talk about n by n square matrix. Let's say we have a square matrix. If the determinant of the square matrix is non-zero, then we say the square matrix A is invertible. Yeah, that's one thing. And let's say if for n by n matrix A exists, there is a n by n matrix B such that A times B equals B times A equals I. Remember what is I? By the way, we use I to represent the identity matrix. Okay, we use I to represent the identity matrix. Then we say B is the inverse of A. So B equals A inverse. Also, A is the inverse of B. A is the inverse of B. So A and B are inverse of each other. So this part, that's the formal definition. That's the formal definition for inverse matrix. This part gives us a way to determine if a matrix is invertible or not. Formal definition for inverse matrix is this part. For any square matrix A, if there is a square matrix B, of course they have to have the same size, such that this is the center of the definition, such that A times B equals B times A equals identity matrix. Then we say A and B are inverse of each other. B is the inverse of A is the inverse of B. Okay, so this is a definition. Again, this is a definition for inverse. We need to know, understand, and remember this condition for A and B are inverse of each other. Okay, so very important. We need to know and remember. We need to understand and remember this condition. A times B equals B times A equals I is the condition for the two matrices A and B are inverse of each other. We focus on finding the inverse for a given invertible matrix. Let's look at example 1. In example 1, we are given a 2 by 2 square matrix, which is 4, -2, 2, 3. We need to find A inverse. I'm going to introduce two methods to solve this problem. Method 1 only applies 2 by 2 square matrix, but method 2 applies any size square matrix. So let's see, how do we find the inverse for A? Firstly, I need to evaluate the determinant of the 2 by 2 square matrix, which is 4, -2, 2, 3. In previous videos, I have introduced how do we evaluate 2 by 2 determinant, right? The green direction, that's the main diagonal. The pink direction, that's the vice diagonal. 4 times 3, 12. Minus the product of the two entries in the vice diagonal. 2 times -2, -4. 12 minus negative, that is 12 plus 4, which is 16. Let me double check. 12 plus 4, yeah, 16. Is non-zero. Means the inverse of A inverse, does exist. We also need this value. So either way, we do have to compute the value for the determinant of A first. And then A inverse is going to be like this. We take the reciprocal of A. We take the reciprocal of the determinant of A, which is 1 over 16. So I'm giving you the formula for finding the inverse for a 2 by 2 invertible matrix. We compute the value for the determinant of the matrix and then take the reciprocal. And then we are going to construct a 2 by 2 matrix here. How do we construct the 2 by 2 matrix here? Very simple. Do you see the two entries in the main diagonal? We are going to interchange the two entries. We switch the positions of the two numbers. It was a 4, 3. Now we switch the order of the two numbers. We got a 3, 4. And then look at the two entries on the vice diagonal. We are going to change those two entries to their opposites. Here we have a -2, right? We are going to write +2 here. We have a +2 here. We are going to write the -2 here. By the way, we are not interchanging the two entries in the vice diagonal. Seems like we are, because it is just an coincident, okay? We are not interchange. We are changing the two entries in the vice diagonal to their opposites. Change the sign in front of the number. -2 becomes +2. 2 becomes -2. Okay? Yeah, let me repeat a rule here. You compute the value for the determinant and take the reciprocal of it and put a number in front of the matrix we are going to construct. How do we construct the matrix? We interchange the two entries in the main diagonal and then change the two entries in the vice diagonal to their opposites. -2 has opposite +2. 2 has the opposite -2. Okay, so actually this is good enough sometimes, depends on the answer choices, but make it even accurate because we are looking for a matrix, the inverse matrix, right? We are not looking for a number times a matrix. So we would have to operate this multiplication. A number times a matrix, we covered that in previous video. 1 over 16 times 3, 3 over 16. 1 over 16 times 2, 1 over 8, reduce. 1 over 16 times -2, -1 over 8. 1 over 16 times 4, 1 over 4. So this matrix is the inverse of A. If you have extra time, you can double check you can multiply A and A inverse. Also A inverse and A. You would see they are equal to each other, and the product is the identity. So I would leave that to you to work on by yourself. It's not a mandatory. If you follow the procedure very carefully, you should have the correct inverse matrix. But if you want to play with it, you can double check by applying the definition that we have just learned earlier. All right, do you like this method? Very fast. This method is pretty fast. However, this method only applies to 2 by 2 matrix. Method 2. We're going to use a different way to find the inverse for the matrix. The method we're going to apply is the elementary row operations. Do you guys still remember the elementary row operations? We have 3 row operations. Interchange 2 rows. Multiply all the entries in one row by a non-zero constant. Number 3, the third row operation is you multiply one row, all the entries in one row by a non-zero constant and add them to the corresponding entries in another row. We applied that, I think is 10.3 maybe, 10.2, yeah. Okay, so this is how do we do that. Firstly, we are going to construct a matrix. A is 2 by 2. I here is the same size identity matrix. So we are creating a 2 by 4 matrix. This is a 2 by 4. 4, -2, 2, 3, 1, 0, 0, 1. So we put a matrix A and the identity matrix together. We make a 2 by 4 matrix. And then we're going to apply the row operation. Only those 3 row operations. For what purpose? For what goal? It's like when you get in your car, you need to know your destination, right? So now we know we're going to apply the 3 row operation. For which goal? We are going to apply the 3 row operation to change this side, this block, you can see that as a block, to the left of the bar as the identity. Okay, so we are going to apply the row operation such that we could change this part as identity, means 1, 0, 0, 1. Let's see how could we do that. So we want a leading one here, right? So I would multiply row 1 by a quarter. That's the second row operation. All the entries in row 1 multiply by 1 over 4. 4 times 1 over 4, 1. -2 times 1 over 4, -half. 1 times 1 over 4, 1 over 4. 0 times 1 over 4, 0. And I copy the second row. I want this number be 0, this entry be 0, because this is a leading one. We want the entry below the leading one be 0. How do we do that? The third row operation. We multiply row 1 by -2 and add it to the row 2. Sometimes the notation is like this. Row 2 minus 2 row 1. So row 1 multiplied by -2 and added to row 2. But as I mentioned earlier, it really doesn't matter because every book, some book they do have different notations. So as long as you understand the operation, that will be fine. You understand that the row 2 is going to be changed. Row 1 remains the same. So we're going to copy the row 1. 1 -half, 1 over 4, 0. Every entry in row 1 multiply by -2 and then add it to the corresponding entry in row 2. 1 times -2, -2. -2 plus 2, 0. -half times -2, which is 1. 1 plus 3, 4. 1 over 4 times negative 2, that is a negative half. Negative half times 0, plus 0, negative half. 0 times negative 2, 0. 0 plus 1 is 1. So far so good? We are getting closer. We want this part be identity, right? We have completed half of them. We are half done. Now I want this number be 1, because this entry is in the main diagonal. How do I do that? I'm going to multiply row 2, all the entries in row 2, by 1 over 4, the reciprocal. So row 1 remains the same. I copy it. Row 2, all the entries multiplied by 1 over 4. 0 times 1 over 4, 0. 4 times 1 over 4, 1. Negative half times 1 over 4, negative 1 over 8. 1 times 1 over 4, 1 over 4. So far so good? Almost there, right? So we only have one thing here to complete the process. We want that entry be 0. In order to reach that goal, we multiply row 2 by half and add it to row 1. Be clear that row 2 will not be changed. Row 1 is going to be changed. We multiply all the entries in row 2 by half, and then add it to the corresponding entries in row 1. 0 times half, 0. 0 plus 1, 1. 1 times half is half. Half times negative, 1 times half is half. Half plus negative half is 0. Negative 1 over 8 times half. Negative 1 over 16. Yeah, maybe you need a scratch paper here. Negative 1 over 8 times half, and plus 1 over 4. And that gives us negative 1 over 16. 1 over 4 is 4 over 16. So that is 3 over 16. And 1 over 4 times half plus 0. That is 1 over 8. Okay, so we finally reached the goal. We got the left-hand side, not the left-hand side, the block to the vertical line as identity. And what happened to the block to the right of the line? And that turns out this actually is A inverse. We are able to find A inverse right here. This is the A inverse. That is A inverse. You can look at the result from method 1. They are exactly the same. Of course, the benefit of this method, applying row operations, not very obvious when we handle a 2x2 matrix. You can see the method 1 works better, is faster. But if the matrix has 3x3, the size is 3x3 or 4x4 or even higher, then this method would be the better one. Okay, so that is example 1. So I'm gonna stop here because already over 20 minutes and continue in the next video.